Hello, this is Mr. Waters, and welcome back. Hope everyone had a wonderful and fun and restful spring break, and I hope everyone is still safe and healthy. I just wanted to let you know that we're starting on a new unit this time around. Right now, we're kind of headed on sort of like the last little leg of the school year, and for most of you, at least the last math leg of your senior year of high school. And I'm going to try to make this one as informative and interesting for you as possible. Okay? Up to this point, we have worked on the first half of calculus, and we've spent some time, a little extra time, exploring it and exploring and working through what's called the differential calculus, which deals with, as I hope you remember, rates of change, derivatives. Okay, and a differential is another word, as you know, for a derivative. Okay, and that was and what we covered were the different ways of taking derivatives. We spent a lot of time, or quite a bit of time, on the applications of derivatives. We did inflection points. We talked about a little bit with related rates, and also optimization problems. I would have liked to have spent a little more time on related rates problems, but I think we kind of got the idea of what related rates are about, and what some of the applications of differential calculus are for. I hope some of you will be motivated to try out a calculus course this next year when you're in college, because you will be totally prepared to do really well in that. Okay, so this is the second half. This is where we begin to see another type of problem that calculus solves. The first type of problem that calculus solves has to do with the rates of change. All the things that we could use derivatives for. All right, slopes of tangent lines and everything that came from that. Right, but the other problem that calculus gets at is it gets at sums and totals, accumulations of things. So, for example, and this is the first example we're going to get at to figure out what this means, is the total distance traveled by a car when it's traveling at a certain rate of speed, or the total energy output for an electrical generating plant for a given year, or maybe the total income earned by a stock as it fluctuates up and down in value over a given period of time, say an entire year. Or here's a physics kind of problem, or really an astronomy problem. One of the earliest problems that calculus attacked was Kepler's second law. Kepler's first law is the famous one, and that is that planets, when they orbit the sun, follow elliptical orbits. The second one, and Kepler wasn't so sure about this, he felt that it was true, but he didn't know how to prove it. And we could visualize this is supposed to be an elliptical orbit, and here's the sun sitting at the focus of the ellipse. Here's the Earth, right, at some point on its orbit. And Kepler's second law says that the total distance traveled by a planet, say the Earth, over an equal period of time, say t, the area swept out, this little sort of pie-pieced area swept out by that planet as the Earth, as it travels in its orbit, is always going to be equal if the amount of time is equal. Right? Now, since the orbit is elliptical, the planet will change speeds. Out here, further away from the sun, it goes a little bit slower. Further in, closer to the sun, it goes a little bit faster, so that it travels further along its orbit here than it will here. But notice that this pi piece here is a little bit longer, so according to Kepler's second law, those two areas are equal. Now, it kind of makes sense But how do you prove that? Well, one of the things that Newton wanted to get at, because he was interested in proving that law, was to be able to show that that law was really true. Okay? So anyway, so these are different kinds of problems that that calculus gets at, is finding sums and totals, not only for regular shapes, but as we will see, for irregular shapes. Now, number one, that's called differential calculus because it has to do with differentials, derivatives. The number two is called integral calculus, because it has to do with sums and totals, what we're going to learn to call integrals. Okay? Now, a little bit of an opinion here. In the beginning, the two fields, integral calculus and differential calculus, were kind of separate from each other. But and I think one of the great achievements of Western thought, the two were brought together. Now, I know what you're thinking. Well, okay, that's just a math teacher, and he thinks math is all important. But based on, well, of course it is, but even more than that, objectively based on the impact that this mathematics here has had on Western technology and Western science, and therefore on Western economics and culture and politics, there's not a lot of things that have had a bigger impact. There's not a single theory or a single concept that's had a bigger impact. Okay, it's one of the great unsung achievements of Western science. Unsung to most people, but it's soon going to be known to us. Okay? And what we're going to get at, this achievement, what I'm talking about, this grand synthesis, it's called the fundamental theorem of calculus. And we're going to go at it actually from two directions. Number one, we're going to start out with the concept of something called an antiderivative. And we're going to go at that in a simple way at first, but it turns out that the process of actually applying integrals and doing integrals has to do with actually being able to calculate antiderivatives. So we're going to start out that today, and we're going to do some simple ones. But also the purpose, what you get from taking the antiderivatives, why you're doing that, why that's important, the problems that it solves, has to do with areas under curves. Okay, and this fundamental theorem of calculus that we're going to get at, that we're going to learn about, puts those two together. And will create this grand mathematical object called an integral that solves so many problems that are important to technology and to science. Okay, so anyway, so we're going to start out first with antiderivatives. Now, I kind of want to set this up, and I want to give you guys kind of a thought problem to start it out. Let's say that I've got this function here, so I better label this here. This is going to be antiderivatives. And as you will see, what I mean by antiderivatives is the operation that's the opposite to taking a derivative. In the same way that multiplication is the inverse operation of a division, or addition is inverse to subtraction, or arc sine is inverse to taking the sign, the antiderivative is the inverse operation to taking a derivative. Now, as you know, we had a bunch of different ways to take the derivative, so it turns out that there's also a bunch of different ways to take the antiderivative. But little things first, okay? So the first derivative rule we learned was the blue pen, was the power rule, right? And so we said if we had something like, I'm going to use a capital F here, if f of x is equal to x cubed plus 3, we could calculate a derivative of that, which would give us the rate of change, of course, the slope of the tangent line. That would mean, and we wrote it, one way to write it was like this, f primed of x, and I'm going to write this another way. I'm going to write little f to represent the derivative of capital F. In other words, f primed. And of course, using our power rule, that was 3x squared. And of course, the 3, being a constant, its derivative is 0. So the derivative is just equal to 3x squared, right? Now that was, okay, or here's another one. Okay, we had something like, and that, well, let's put that in as a rule now. So we said, well, the power rule was that if our original function f of x was equal to ax to the n, then f primed of x, that's supposed to be an n there, ax to the n, f primed of x, which we're going to call sometimes little lowercase f, that was n times a times x to the n minus 1, right? We multiplied the coefficient in front to get the new constant, or, you know, we multiplied the exponent in front to get the new coefficient, and then we subtracted 1 from the exponent, right? And that was a pretty, as it turns out, a pretty easy rule to enact. So if we had something like capital G of x, if that was equal to, say, negative 4x squared plus 2x, then capital G of x, which using our slightly new system here, I'm going to call that capital G primed, or little g of x. Got a reason for doing that. It'll be clear later. 8x plus 2, right? Multiply the coefficient, the exponent in front to get the new coefficient. Subtract 1 from the exponent, right? And then we had other kinds of derivative rules besides the power rule, of course. For example, if we had p of x was equal to sine x, then we knew that the derivative, capital P primed of x, or little p of x, was equal to cosine x, right? That's pretty simple. Now the concept of an antiderivative is simply that, what if we had a situation where we're starting with a function with one of these over here? And the question is, okay, what's the bigger function that if we took the derivative of it, we'd end up with this one? That's the antiderivative, right? So in other words, if we were starting out with little f of x is equal to 3x squared, what's the function, capital F, that if we took the derivative of it would end up with 3x squared? Okay, well, let's think about that, right? And that we already knew, because we did it the first way, turned out to be x cubed plus 3. Does that make sense? Okay, so that's what we're getting at. So we're going to learn, part of what we're going to learn is this business here of taking antiderivatives, okay? But first, I want you to think about what the antiderivative power rule is. There's a rule for derivatives. That's this one right here. That's the derivative power rule. It turns out that if we're starting with a function that we already know is the derivative and we want to work backwards to get the antiderivative of it, turns out there's a rule for that also. And I want you to kind of think about it for a second. Let's keep in mind that, give us first, you know, I'll tell you what the rule is, but I want to see if you can look at the examples we've given here, just the power rule ones, don't worry about the sine and the cosine one, okay? If we're already given this derivative here, how do we work backwards to what the original function is? Okay? Now, I'm going to give you a minute to ponder that. I'm going to say, what if we've got t of x? And I happen to know that that's 8x cubed. Can you name a function? I want you to think about this. I want you to put the video on pause right now. And I want you to think of a function, call it capital T of x, that if we took the derivative of that function, the result would be 8x cubed. Okay, put the video on pause and spend a minute thinking about that and see if you can figure out what it is. Okay, pause now. Okay, you're back. Hopefully you thought of it. Okay? If you got 2x to the fourth power, then you would be correct. Because if you take the derivative of this, 4 times 2 is 8, and then give us the new coefficient, and then subtract 1 from the 4 to give us 3, that would give us the antiderivative. Keep in mind. Now, if you said, on the other hand, if you said, oh, Mr. Waters, it's 24x squared, well, that's the wrong answer to that's the right answer to the wrong problem. Okay, that's just the derivative of that, right? We want to know the function that if we took the derivative of it, that's this one, the red one, we would get that one there. That's called the antiderivative, and it's the inverse operation of the derivative. Okay? All right, so let's try another one. I'm going to say 12x squared, no, 12x cubed. Try that one. Probably should have it in black here to be consistent. 12x cubed. Name a function that if you took the derivative of it, the result would be 12x cubed. Put the video on pause and spend a minute thinking about that. Okay, you're back. Well, how do we know what it is? Well, because in order to get the derivative, we know that we have to subtract 1 to get the 3. So to work backwards, that means we're going to be adding 1. So that means that the derivative function is going to be x to the fourth power. Yeah? Okay, and then we're multiplying something in front by 4 to get 12. Well, that would have to be 3. So if this function is little f of x, the derivative, then this function here is big f of x, the antiderivative. Okay? So, and in fact, there's a formula, just like there is for the power rule. It turns out that in the world of integrals, unlike derivatives, there's not a lot of formulas. But this one has a formula, okay? And it goes like this. If f of x is equal to ax to the n, then its antiderivative, f of x, big F of x, is equal to a to the n plus 1 to the x to the n plus 1. We added 1 because we're working backwards to the bigger function rather than subtracting 1 like we did with the derivative. And notice here, how did we get from 12 to 3? Well, we divided over here. We divided 12 by 3 plus 1. So 3 plus 1 goes there. 12 divided by 3 plus 1, 12 divided by 4 is equal to 3. Okay? So this is our first, and you guys want to make note of this, that's our first antiderivative formula. So that'll be the first part of our work today. We'll be able to find some antiderivatives for power functions. And just like the derivative formula works for any power function, the derivative power formula works for any power function to find the derivative. The antiderivative power function works for any power function to find the antiderivative. So let's try a couple of examples here using the formula. Then I'm going to post some classwork which you should try out to make sure you've got this down. And then this part here is going to be the first part of the homework. Okay? All right, so let's see here. So, okay. So number 1, let's try this one. Now I'm going to introduce a strange and terrible symbol. It looks like this. It looks like a really interesting script S. Now it turns out we're going to learn all about what that means. But that means, for our purposes, that means find the antiderivative. Okay? And we're going to have, in your classwork, there's some symbolism that was put in there that may not be perfectly clear right now, but don't worry about if it's not. This symbol right now is just going to mean find the antiderivative. Okay? It means much more than that, along with, but this is going to be a good start for us. So let's say we had something like 3 times x. I'm going to put 3 times x just like that, right? So we want to find the function that if we take the derivative of it, our answer would be 3x. Well, okay, we're going to appeal to this formula here. The a is 3, and the n is 1. So it's going to be, over here, 3 over, so n is equal to 1, and a is equal to 3, right? 3 over 1 plus 1, x to the 1 plus 1, or 3 over 2, x squared. Now, how can you check your work? Well, take the derivative, right? Because if it really is inverse, I should be able to start with this, use our regular derivative power rule, and get 3x back again. Well, you can see that works. 2 times 3 over 2, the 2's cancel, it's leaving just the 3. 2 minus 1 is 1. Yeah? Okay, good. How about this one here? Number, how about negative 6x to the 7th? Okay, well, okay. So the antiderivative, and again, this weird little s means find the antiderivative. Negative 6x to the 7th power, that's going to be x to the negative 6, and you see here that the n is 7, so 7 plus 1 to the 7 plus 1. There's an n plus 1 in both spots, right? So that's negative 6 over 8 x to the 8th power, right? 6 over 8 reduces to 3 over 4, so that's negative 3/4 x to the 8th power. You can see that if we take the derivative, we multiply 8 in front, 4 cancels out, we've got 2 times 3 is negative 6, 8 minus 1 is 7. So that's the antiderivative of that. Okay, it works even with something like this, say 2/3, see, let's not have a fraction yet. Get ready for super complicated arithmetic. Let's say it's 4x to the negative 2 plus 3x squared. Okay, well notice, and then on our work here, those will be in parentheses because it's all one number. So just like we do with derivatives, if we're adding them, we just do the antiderivative separately. So I'm going to take this is n right here, and here's a for the first power part, and down here it's going to be 4 on top and negative 2 plus 1, it's n plus 1 x to the negative 2 plus 1, right? Simplifying, that's 4, that's negative 4 over 1 x to the negative 1, or negative 4 x to the negative 1, right? Well, does that, okay, so then here, on the second part, I'll put that here. This is 3 over 2 plus 1 x to the 2 plus 1. 2 plus 1 is 2 plus 1 is 3, so that's 3 over 3. So that is going to be 1x. 2 plus 1 is 3, right? Now check our work. Well, take the derivative. Negative 1, so the derivative power rule says negative 1 times negative 4, positive 4, negative 1 minus 1, negative 2. Oh yeah, that's worked. Okay, and then for this one here, 3 times 1 is 3, 3, and then 3 minus 1 is 2. So we're using this rule here. Guys get that? Okay, very good. Now there's one more tiny detail, and it's an important nuance. I'm going to go back to number 1 here. And then once we cover this one little bit here, one little bit of formalism, I'm going to turn you loose to try out the classwork and maybe the other video. Okay? So, let's say we were starting with 4x squared, right? And let's say that was capital F of x. And this is, let's say we also had f of x is equal to 4x squared plus 3, or f of x is equal to 4x squared minus 1, or f of x is equal to 4x squared plus pi, which of course is a number. Now, those are the capital F's. These are the antiderivatives. Now, let's say we take the derivatives of these. Well, that one is 8x. This one, the 3, is a constant, so that one is an 8x. This one is 8x, but negative 1 is a constant, so it's equal to 0. This one is 8x. Pi is just a number, so it's a constant. So all 4 of these functions, capital F's, even though they're actually different functions, when you take the derivative, because this constant on here zeroes out, the derivative works out to be the same. So what if this is your problem? You're supposed to find the derivative of that. You're supposed to find the antiderivative of that. You're supposed to find some function f that is the antiderivative of this. Well, which one is it, right? Using our power rule, right, up here, that would be 8 over, because the coefficient there, the exponent there is 1, so that's 8 over 1 plus 1, x to the 1 plus 1. Well, we're getting 4x squared, which, yeah, okay, that's the polynomial part here. But how do we know which constant to put in? Well, we don't. So here's the thing. Whenever you take an antiderivative as an important and necessary and will be marked wrong if you don't put it, part of the answer, I'm going to put plus c. This plus c represents all the potential coefficients of, constant coefficients we could have on the end here, including 0, right? so that if we start with this and we take the derivative, this constant here, which is just a number, cancels out and gives us the 0, and then we just get 8x as the derivative, right? So all of these answers up here, I didn't put them because I hadn't told you about this little bit here. When I write my final answer, I'm going to put plus c after all of them. And you've got to do that too when we do the antiderivatives. Okay, so that's all for this one. And the next part, we're going to do a little bit about areas under curves. But for now, check out the antiderivative classwork and maybe the first part of the homework. Bye.